So now that we know a little bit about chemical energy and what we call enthalpy, we're going to look at something called Hess's law. Hess's law states that if a reaction is the sum of two or more other reactions, the delta H, or the change in enthalpy, for the overall reaction is the sum of the other delta H's. So if a reaction is made up of multiple steps, each step has a particular delta H. The total delta H for the overall reaction is the sum of all the other delta H's. So that's what we're going to be calculating. We're going to calculate the overall change in enthalpy for a particular reaction, and you'll be given the reaction steps and their corresponding enthalpies. So the trick is just to rearrange the reactions to get from your pieces to what the big picture is. So let's work through some examples. Our first example involves the change of carbon in the form of diamond to carbon in the form of graphite. Now, carbon doesn't just automatically switch from diamond to graphite. It actually reacts with oxygen to produce carbon dioxide, and then from there goes into graphite. So we're going to look at the reactions that make that happen. So here's our goal reaction. Carbon in diamond form goes to carbon in graphite form. That's what we're trying to find the delta H for. Our two partial reactions are carbon as diamond reacting with oxygen to produce carbon dioxide, and that has an enthalpy, or a delta H, of negative 395.4 kilojoules. So it releases, when it goes through that process, it releases 395.4 kilojoules of energy. And then our second reaction is carbon in the form of graphite reacting with oxygen to produce carbon dioxide, and that reaction releases 393.5 kilojoules of energy. Now, the first thing you want to do when you go to do a Hess's law style problem is to compare your overall reaction to your two sub-reactions, or two other reactions that we're going to use. We're going to use these two to get to our goal. First thing I notice is that our goal reaction doesn't involve any oxygen or carbon dioxide. That means in this process, we need to get rid of the oxygen and the carbon dioxide. They're going to cancel out. Things cancel in chemical reactions just like they cancel in other types of equations. If you have things on both sides of an arrow, they're going to cancel out. So that's our goal. We're going to try and cancel out our oxygen and our carbon dioxide. The other thing that I notice is we start with diamond and end with graphite. This reaction shows starting with diamond. So I'm going to copy that reaction just as it is. So I'm going to say carbon, then I'm going to shorten this to just a D, plus oxygen forming carbon dioxide. And I'm going to go ahead and copy the delta H down here. Now our second reaction, I notice it has graphite as a reactant. But graphite isn't a reactant in our goal reaction. It's a product. So I need to flip this entire reaction. So my product is going to become my reactant. So I'm going to start with carbon dioxide, and then my reactants are going to become my products. So I'm going to end with carbon in graphite form and oxygen. Since I flipped the reaction, I have to flip the sign of the delta H. So instead of this being a negative number, this is going to become a positive number. So instead of it being negative 393.5 kilojoules, I now have a positive 393.5 kilojoules. Now, if I'm treating this similar to a math equation, I'm really just going to add everything up. So if I look at this, I have carbon in the form of diamond plus oxygen plus carbon dioxide goes to carbon dioxide plus carbon in the form of graphite plus oxygen gas. Now I need to cancel out, just to check and make sure I've reached my goal equation, things that show up on both sides of the arrow. So I have oxygen on both sides and I have carbon dioxide on both sides. So I've reduced this down to carbon in the form of diamond to carbon in the form of graphite. So see how I went through this process? I rearranged my reactions. I flipped this one, added everything together, simplified, made sure I canceled out things on both sides of the arrow that were the same, and I ended up with what my goal reaction was. Since I did this, I can simply add up my two delta H's. So I have negative 393.4 plus a positive 393.5 kilojoules. And overall, that gets me negative 1.9 kilojoules of energy. And that would be my answer, because you're looking for the delta H of this overall reaction given these two subreactions. Let's look at a second example. So in our second example, we want to find the delta H for two aluminums reacting with iron 3 oxide to produce 2 irons and 1 aluminum oxide. So again, I'm going to compare the two given reactions with their given delta H's to my overall goal reaction. The first thing that I notice is that I want aluminum as a reactant. This first reaction is the only reaction that involves aluminum, and it already has aluminum as a reactant. So I'm going to leave this reaction alone, and I'm just going to copy it right down below. And then I'm also just going to copy its delta H. The other thing I notice is that my other reactant is my iron 3 oxide. Well, there's no iron 3 oxide in this first reaction. The iron 3 oxide is in the second reaction. But it's in the second reaction as a product. I need it as a reactant. It's given as a product. So I need to flip this whole reaction. So my products are going to become my reactants. And my reactants are going to become my products. And then, since I flipped the reaction, I also need to change the sign on my delta H. So now I'm going to add my reactions together. So to cut out a step, I'm going to go straight to canceling out things on both sides. So I notice that I have 1.5 oxygens here, and I have 1.5 oxygens down here, so I'm going to cancel those out. And then I'm left with everything else is just the same, so it doesn't have a partner on the other side to cancel with. So I'm just going to copy everything down. So I have 2 aluminums plus an iron 3 oxide and that matches my goal reaction. My goal reaction had aluminum and iron 3 oxide as my reactants. I have aluminum and iron 3 oxide as my reactants. And then my goal reaction had 2 irons and aluminum oxide as my products. I still have 2 irons and aluminum oxide as my products here. So since I have my goal reaction, now I just need to add my delta H's together. So I have negative 169.8 plus a positive 824.2 kilojoules. And that gets me an overall, ooh, I copied something down wrong. This should be 1,669. Ooh, no, that's really hard to read. Kilojoules, 1,669.8 kilojoules of energy. I apologize, that was a typo. Because my overall should be a negative 845.6 kilojoules of energy. So this first reaction was negative 1,669.8 kilojoules. My second reaction was 824.2 kilojoules, which gets me an overall negative 845.6 kilojoules of energy. Let's look at our next reaction. So in this one, the goal is lead 2 chloride reacting with chlorine gas to produce lead 4 chloride. And we have our 2 given reactions. So I want you to work through this one and see what you get for the overall delta H for this reaction. Then we're going to come back and check our answer. Okay, let's check and see what we got. So I noticed that in this reaction, I need lead 2 chloride as a reactant. Now lead 2 chloride shows up in my second reaction, but it's as a product. So I'm going to flip it and make it go the other way. So my lead 2 chloride is going to become my reactant, and my lead and my chlorine gas are going to become my products, which means I need to flip the sign on my delta H. And then I also noticed that I need lead 4 chloride as a product. My first reaction is the only one that has the lead 4 chloride, and it's already as a product. So I'm going to go ahead and just copy that reaction down as it is. And then I'm also just going to copy its delta H. So now if I add my reactions together, my leads cancel because there's a lead on each side of the arrow. My lead 2 chloride doesn't have a partner because this one is lead 4 chloride. My chlorines, though, I have chlorine on both sides, but I'm going to use one of my chlorines to cancel here, which is only going to cancel out one of my chlorine gases on this side. So I'm still left with a chlorine gas reacting with the lead 2 chloride to produce the lead 4 chloride. So they don't necessarily have to have equal coefficients, but you have to keep in mind you can only cancel the smallest number. So I can only cancel one of my chlorine gases, and so I'm still left with another chlorine gas. Now I'm going to add my delta H's together, and you should get an overall, I copied something down again, wrong again, should be 359.4, goodness, 359.4, because you should get an overall positive 30.2 kilojoules of energy. So this is an endothermic reaction that requires an overall 30.2 kilojoules of energy to make it happen. Now, we didn't go through a type of example that I'm about to mention, but sometimes you have to multiply to get things to cancel correctly. So if you have to multiply an entire reaction by a coefficient in order to get certain things to cancel to get to your goal reaction, you also have to multiply your delta H. So say, for instance, our goal reaction didn't have the chlorine. I would have to multiply this entire top reaction by 2 so that I could get rid of both of my chlorine gases. Sometimes you have to do that, and you'll see examples like that in your homework.